In this video, I'm going to introduce you to scalar quantum electrodynamics. The first goal of this video is to give you a detailed description of how to construct the Lagrangian density of scalar QED. The other goal of this video is to show you how to repurpose skills you've learned previously from this lecture series to quantize scalar QED based on that Lagrangian density. So let's jump into the math section. To be clear, the math in this video is in natural units. The central idea of scalar QED is to replace the massive electrically charged spinors in normal QED with massive electrically charged scalars. We can construct such a theory by performing exactly the same process on the Klein-Gordon complex massive scalar Lagrangian as one does with the Dirac Lagrangian to obtain standard QED. If you aren't familiar with the construction of the standard QED Lagrangian, then I encourage you to watch my video on that, link in the description. However, I will give a brief summary here. When deriving the standard QED Lagrangian, we began by noting the existence of a global U1 symmetry. We then explored the possibility of upgrading that symmetry to a local symmetry. The Dirac Lagrangian isn't naturally locally U1 invariant because of the derivative term, however. We then concocted a new derivative operator which contained a vector field whose transformation under U1 cancelled the unwanted term yielded by the partial derivative term under local U1 transformations. The way this vector field needed to transform in order to yield local invariance matches the gauge transformation of the electromagnetic 4-vector potential under which electromagnetism is invariant. We were then free to identify the gauge field in this new operator with the electromagnetic 4-vector potential and add the free Maxwell Lagrangian on as the kinetic term for the new gauge field, where that vector field in the new derivative operator is what I mean by the gauge field. I think I forgot to say that earlier. Extracting the interaction Lagrangian from this QED Lagrangian, we then observed that the coupling that was produced by making the Lagrangian locally U1 invariant was simply proportional to the U1 Noether current density contracted with the 4-vector potential. Comparing this to the standard interacting Maxwell Lagrangian density then allowed us to identify the U1 Noether current density with the electromagnetic 4 current density. This completed the process. We can perform exactly the same process in the Klein-Gordon complex massive scalar Lagrangian, which I will call the KG Lagrangian for short, to yield a scalar analog of standard QED because the KG Lagrangian possesses the same global U1 invariance as the Dirac Lagrangian. The KG Lagrangian is this, if you remember. We can clearly see that it is invariant under the following global U1 transformation, where lambda is a constant, which naturally means that phi bar, which is just the complex conjugate of phi, transforms like that. So you can see these factors here and the Lagrangian just cancel against each other, leaving it invariant. Clearly, phi and phi bar have opposite charge under U1, which you can see by looking at the factors that give their transformation. The standard calculation yields the following conserved Noether current density from this global U1 symmetry, this current density right here. One can also clearly see that if this transformation were taken to be local, the derivative term would not be invariant because these factors would no longer just pass through the derivatives. However, if one introduces the following new derivative operator called the gauge covariant derivative, where this vector field is called the gauge field, where it transforms under U1 like this, then we find that the derivative actually does transform the way it needs to under local U1 gauge transformations in order for the action to be invariant if we substitute those derivatives in. A similar calculation gives us this result for the gauge covariant derivative of the phi bar field, the complex conjugate field, and as I said, we can now see that substituting this covariant derivative in for the normal derivative would lead the KG Lagrangian to be locally invariant, which just gives us this Lagrangian, which I called KG inv, where inv is short for invariant. Now that we have upgraded to a local symmetry, we must recalculate the U1 current, and we get this result. Of course, local symmetries don't yield any new conserved charges, but this formula will make it easier to identify the electromagnetic current density later. As stated above, we can then notice that A mu, called the U1 gauge field, transforms like the electromagnetic 4-vector potential and identify it with that. We can then add the free Maxwell Lagrangian on as the kinetic term for the gauge field, thus yielding the following result for the scalar QED Lagrangian. This is the gorgeous theory itself that we're after, where of course we have the normal field strength tensor. Inserting the formulas for the covariant derivatives and inspecting gives us this interacting Lagrangian density, and if we look up at that local U1 current, we find that we can rewrite it like this. And then if we compare that to the interacting Maxwell Lagrangian, we see that we can just identify this with the electromagnetic 4 current density, and also we can identify Q as the electric charge strength associated with the scalar field, and also, as we will see shortly, and as we saw in my quantization of a free complex scalar field, Q is the charge of the scalar field quanta, or rather the charge magnitude. Of course, there's two kinds with opposite charge. Remember that the local U1 current yields no physical conserved charges beyond that produced by the global U1 conserved current. Specifically, the charges computed from both are identical on shell. With the Lagrangian of the theory established, we can move on to the quantization of the theory. I have made a video explaining how to quantize a free complex scalar field, and I have made 2 videos explaining how to quantize a free electromagnetic field in different ways, in the Coulomb gauge and via the Gupta-Bleuler technique. I have also made a video showing how to use the mathematics of free field quantization to quantize an interacting quantum field theory. That video is called the Interaction Picture S Operator S Matrix Quantum Field Theory, with bars separating those things. There are links to all of these videos in the description. For full details, you should review those videos. However, I will give a summary here covering all of the most important details from them. The free massive complex scalar Lagrangian that we quantized was already given above, but I will give it again for convenience. It's just this. I called it the kg Lagrangian for short. The equations of motion work out to be those. With the free complex scalar field, we started with these solutions, which then gave these results for the conjugate fields, and then we imposed these canonical equal time commutation relations. This caused the Fourier coefficients to behave like creation and annihilation operators for 2 different kinds of states, where this is the formula for the Hamiltonian, and we have these E states being energy eigenstates. We found that only positive energy states were possible, and that the 2 different types of states have opposite charge. This leads us to the interpretation that these were particle states of 2 different charges. Specifically, we had the following discussion concluding these things. The Hamiltonian, where n stands for normal ordering, is an integral over this kind of term and this kind of term, so its expectation values are non-negative. With this in mind, because a of k and b of k lower the value of the eigenvalue by 1 quantum, there must be a lowest state that gets zeroed by both a of k and b of k, so we have these results. This ground state will be taken as the definition of the vacuum because it has no quanta of energy left to be annihilated. Now that we have this particle interpretation, we can figure out what's different between the 2 types of particles. Specifically, we can identify them as having opposite U1 charge. We can do this because we can insert the quantum fields given above into the U1 charge given in the last section. If it isn't clear, to get the charge, I integrated over the charge density, where the charge density is the 0 component of the 4 current, and it's the 4 current that I actually gave in the last section. Then we can apply this operator to the energy eigenstates to yield these results, which shows that those states do have opposite U1 charge, specifically Q and minus Q. We can actually identify these particles as antiparticles of each other, but because we haven't yet coupled the scalar field to the electromagnetic field, we don't yet have a theory containing the concept of annihilation. And with this, we have completed the summary of quantizing a free complex scalar field. Now on to free electromagnetism. When doing perturbative quantum field theory, one usually uses the covariant Gupta-Bleuler quantization scheme for quantizing the electromagnetic field, so that is the scheme that I will summarize here. In Gupta-Bleuler quantization, we add a gauge-fixing Lagrangian to the standard Maxwell Lagrangian to allow the covariant commutation relations to be imposable. Specifically, we have this. This Lagrangian can then be rewritten in the following way using a bunch of integration by parts, where this p mu nu tensor is this. We then selected the gauge parameter alpha to be equal to 1 and integrated by parts one last time, leaving the Gupta-Bleuler Lagrangian, which had this form and these equations of motion. The general solution to these equations of motion that we considered was this, and then of course that gave this result for the conjugate fields. We could then impose these covariant equal time commutation relations. We then found that the Fourier coefficients could again be interpreted as creation and annihilation operators, this time for photons. The particle interpretation comes from the same rationale as with the scalar case given above. We then imposed the following physical state condition to allow us to exclude temporal and longitudinal ghosts from the Hilbert space, this one. From here in my interaction picture video, I showed how to use such free field mathematics to quantize an interacting field theory. Specifically, we found that the probability of one free asymptotic initial state transitioning to some free asymptotic final state is given by this matrix element where we have this formula for the S operator and where the interacting Hamiltonian density for scalar QED calculated via the normal method works out to be this. Remember that because this is the interaction picture, H prime I is to be written in terms of the free quantum fields given above. The subscript I indicates the interaction picture and the prime denotes that it is the interacting part of the Hamiltonian, in case that wasn't clear, where if the free conjugate fields written in terms of the scalar field are inserted, this can be simplified to this, where we have that non-covariant term. This is important because inserting the interacting field theory values of the conjugate fields flips the sign on the non-covariant term. We are free then to Taylor expand S, Wick expand it, and work on evaluating individual terms in the S matrix, which in general may require the LSZ reduction formulas. During this evaluation, one would find that the effect of the non-covariant term cancels against that produced by another source of non-covariance, the chronological products of derivative terms. One can find a formal proof of this in Itzikson and Zuber on page 284. Now on to the Feynman rules derivation. I showed this process for the case of standard QED in my video on deriving the Feynman rules for standard QED. There is a link to that video in the description along with all of the others. The process for scalar QED is the same. One is merely working with a different interacting Hamiltonian with partly different field content, scalars instead of spinors. Also in that video we learned that the terms in the scattering amplitude, and particularly its most frequently encountered cousin, the Feynman amplitude, have a very patterned structure. This structure naturally allows the terms in the Feynman amplitude, and therefore the scattering amplitude or S matrix, to be written out from algorithmically listable Feynman diagrams using Feynman rules. Given that nothing but the specific interacting Hamiltonian causes the S matrices of different quantum field theories to be different, such Feynman rule diagram patterns can be identified for any quantum field theory via the same process as given in that video on deriving them for normal QED. If one bothers to go through the same process again for scalar QED, one gets all of these results here. With the Feynman rules written out, this review of scalar QED is now complete. So now you know how to construct the Lagrangian density for scalar quantum electrodynamics. It's very similar to normal QED, as you saw. And you also know how to repurpose skills that you've learned previously in this lecture series to quantize scalar QED given that Lagrangian density.